April 21st, 1945. Kummersdorf Proving Ground, Brandenburg, Germany. The Third Reich was dying in flames around them, yet American forces advancing through the smoking ruins of Hitler's industrial empire were about to discover something that would challenge everything they thought they knew about German engineering capabilities. Staff Sergeant Robert Chen of the 751 Tank Battalion picked his way through the debris-strewn courtyard of what had once been Germany's premier tank testing facility. The acrid smell of burnt fuel and cordite hung in the cold morning air. Twisted metal and shattered concrete told the story of desperate German attempts to destroy evidence before fleeing. But something beneath the rubble caught Chen's attention, something that didn't belong to be a massive concrete. What appeared bunkers stretched across the testing yard, covered by torn camouflage netting and hastily poured cement slabs. Chen called over Lieutenant Colonel James Morrison, the technical intelligence officer assigned to catalog captured German equipment. Morrison had spent months documenting abandoned German tanks and weapons, but as he approached this particular structure, his trained eye detected something unusual. The concrete wasn't solid. It was covering something underneath, something enormous. The two men began clearing debris with the help of their squad, expecting to uncover another destroyed building or perhaps a buried fuel depot. What they found instead defied comprehension. Emerging from beneath the camouflage was not concrete or stone, but steel. Massive steel plates joined by rivets the size of dinner plates. As more debris fell away, the true scope of their discovery became apparent. They were looking at armor plating thicker than anything either man had ever seen. Morrison ordered his men to continue clearing the area while he radioed for additional personnel and equipment. Within hours, a full technical evaluation team had arrived from the advancing Allied forces, including engineers from the Aberdeen Proving Ground and captured equipment specialists who had been following the American advance specifically to document German technological developments. What they uncovered over the next several days would fundamentally alter Allied understanding of German tank development and Hitler's final desperate gambles. The object beneath the debris was indeed a tank, but calling it a tank seemed inadequate for describing the mechanical monster they had discovered. The vehicle stretched over 33 feet in length and stood nearly 12 feet tall. Its tracks, each link forged from solid steel, rose higher than a man's head. The turret alone was the size of a small house, mounting a gun barrel that extended nearly 20 feet beyond the vehicle's front armor. American engineers had examined hundreds of German tanks throughout the war, from the lightweight Panzer IIs captured in North Africa to the formidable Tigers encountered in Normandy. This machine dwarfed them all. Technical Sergeant William Hayes, a mechanical engineer from Detroit who had been drafted into the Army's Technical Intelligence Service, spent 3 days measuring and documenting the vehicle's external dimensions. His notebook filled with figures that seemed impossible. The front armor measured 200 millimeters thick in some sections, nearly 8 inches of solid steel designed to stop any projectile the Allies could fire. The side armor, while thinner, still exceeded the frontal protection of most Allied tanks. The vehicle's estimated weight approached 200 tons, more than 4 times heavier than the American Sherman tanks that had formed the backbone of Allied armored operations. The main gun presented another engineering marvel that troubled the American evaluators. The 128mm cannon represented a leap in tank armament that exceeded anything in Allied arsenals. Technical analysis revealed that this weapon could penetrate the frontal armor of any Allied tank at ranges exceeding 2 miles. The secondary armament, a 75mm gun mounted coaxially with the main weapon, matched the primary armament of most Allied tanks. This single vehicle possessed more firepower than an entire American tank platoon. But the most disturbing discovery came when the evaluation team managed to access the vehicle's internal systems. German engineers had designed this machine using a revolutionary propulsion system that combined diesel engines with electric drive motors. The concept, borrowed from naval engineering, allowed the massive vehicle to achieve precise maneuvering despite its enormous weight. Mercedes-Benz had provided a specially modified V12 diesel engine that generated electrical power for motors driving each track independently. American engineers recognized the sophistication of this system while simultaneously grasping its fundamental impracticality for field operations. Inside the vehicle, cramped crew compartments revealed the human cost of German engineering ambitions. Despite the machine's massive external dimensions, the interior space remained severely limited due to the enormous thickness of the armor and the complex mechanical systems required to operate such a behemoth. The crew positions showed evidence of incomplete installation, with exposed wiring and unfinished control panels, suggesting the vehicle had never reached operational status. German technical manuals recovered from the site indicated that operating this machine would require specialized training and constant mechanical attention from highly skilled technicians. The discovery team found additional disturbing evidence in the form of technical drawings and planning documents scattered throughout the facility. These papers revealed that the massive tank they had discovered, designated by the Germans as the Panzerkampfwagen VIII Maus, represented only the beginning of Hitler's supertank ambitions. Engineering studies detailed plans for even larger vehicles, including the E-100 program and the nightmarish P-1000, a proposed Ratte, 1,000-ton land battleship that would have mounted naval artillery. American intelligence officers studying these documents realized they were examining the final desperate attempts of a regime that had lost touch reality. The resources required to produce even with military, a handful of these supertanks could have equipped dozens of conventional armored divisions. The steel allocation alone exceeded the monthly production capacity of several American tank factories. Yet German leadership had pursued these projects even as their conventional forces faced critical shortages of basic equipment and supplies. The technical evaluation revealed fundamental flaws that would have made these vehicles militarily useless, even if Germany had possessed unlimited resources to produce them. The Maus consumed fuel at rates that would have required a dedicated supply train simply to keep a single vehicle operational. Its maximum speed of 12 miles per hour made it vulnerable to air attack and unable to participate in the mobile warfare that characterized modern armored operations. Most critically, the vehicle's weight exceeded the capacity of virtually every bridge in Europe, severely limiting its operational mobility. Perhaps most tellingly, the engineering analysis revealed that German designers had solved complex technical problems while ignoring basic operational requirements. The electrical drive system represented genuine innovation that would influence post-war tank development. The armor protection exceeded anything previously achieved in mobile vehicles. The main gun could destroy any existing tank, yet the complete vehicle remained essentially immobile, consuming resources that could have produced dozens of conventional tanks while providing no practical military advantage. The American engineers documenting this discovery understood they were witnessing the physical manifestation of a regime's final delusions. Hitler's obsession with technological supremacy had produced a machine that was simultaneously a masterpiece of engineering and a monument to strategic failure. The Maus represented German industrial capability pushed to its absolute limits in service of a concept that violated every principle of practical military engineering. The examination continued through the following weeks as specialized teams arrived from Allied technical intelligence units. Major Harold Fitzgerald, chief engineer from Wright Field's Foreign Technology Division, had been assigned to oversee the complete evaluation of captured German equipment. His team included metallurgists, automotive engineers, and weapons specialists who possessed the technical expertise to understand what German industry had achieved in its final months. What they discovered challenged fundamental assumptions about the limits of mechanical engineering. The vehicle's construction revealed manufacturing techniques that American industry had never attempted at such scale. Each armor plate has a single piece, requiring been forged as hydraulic presses of enormous capacity and precision heat treatment facilities that exceeded most American industrial capabilities. The turret alone weighed 65 tons, more than twice the weight of an entire Sherman tank. German engineers had somehow solved the engineering challenges of mounting and rotating such massive structures while maintaining mechanical reliability under combat conditions. Detailed examination of the electrical systems revealed innovations that would influence American tank development for decades. The Mercedes-Benz MB-509 diesel engine generated power for electric motors that drove each track independently, providing maneuverability that conventional mechanical transmissions could not achieve. This diesel-electric configuration, borrowed from naval engineering, allowed precise control over the massive vehicle's movement despite its enormous weight and inertia. American automotive engineers recognized the sophistication of this approach while simultaneously calculating the astronomical fuel consumption such a system would require. The main armament presented another technological specialists. The 128mm leap that troubled Allied weapons' KWK-44 cannon represented the culmination of German artillery development, capable of penetrating any existing Allied armor at ranges exceeding 3,000 meters. The weapon's loading mechanism incorporated automated systems that reduced crew requirements while maintaining rapid rates of fire. Technical analysis revealed that a single shot from this gun could disable multiple Allied tanks through overpenetration, passing completely through one target to engage others behind it. But the most disturbing discoveries emerged from examining captured German documentation found throughout the facility. Technical drawings and production schedules revealed that the Maus represented merely the first step in Hitler's escalating obsession with super-heavy armored vehicles. Engineering studies detailed the E-100 program, which would have produced tanks weighing 140 tons with even thicker armor protection. More shocking still were preliminary designs for the P-1000 Ratte, a 1,000-ton land battleship that would have mounted twin 280mm naval guns in a rotating turret. These documents revealed the complete disconnection between German leadership and military reality. Resource allocation studies showed that producing a single Maus required steel quantities sufficient for manufacturing 40 conventional tanks. The specialized tooling and factory modifications necessary for super-heavy tank production consumed resources that could have equipped entire armored divisions with reliable, proven vehicles. Yet Hitler had personally approved these programs even as German forces faced critical shortages of basic equipment, ammunition, and fuel. American intelligence officers studying captured German records discovered that internal opposition to these programs had existed throughout the German military establishment. Field commanders had repeatedly requested conventional tanks that could be produced quickly and maintained easily under combat conditions. German tank crews had reported that existing heavy tanks like the Tiger II already exceeded the practical limits for battlefield operations due to mechanical complexity and fuel consumption. These concerns had been systematically ignored by leadership obsessed with technological superiority over operational effectiveness. The human cost of operating such machines became apparent through examination of crew training materials and operational procedures. The Maus required a crew of 5 highly trained specialists, each responsible for complex systems that demanded constant attention and adjustment. Driver training alone required months of instruction on electrical systems, hydraulic controls, and precision maneuvering techniques necessary to prevent mechanical failures. Radio operators needed specialized knowledge of communication equipment powerful enough to penetrate the vehicle's massive armor plating. Gunners required extensive training on fire control systems more complex than those used in naval artillery. Perhaps most revealing were the maintenance requirements documented in German technical manuals. Routine service procedures required specialized equipment, precision tools, and replacement parts that could only be manufactured in dedicated facilities. Field repairs demanded highly trained mechanics with extensive knowledge of both diesel engines and electrical systems. The technical complexity made battlefield maintenance virtually impossible, meaning that mechanical failures would result in permanent loss of the vehicle regardless of battle damage. Transportation presented insurmountable logistical challenges that German planners had never adequately addressed. The vehicle's weight exceeded the capacity of virtually every bridge in Europe, forcing movement to follow predetermined routes that eliminated tactical flexibility. Railroad transportation required specially reinforced cars and modified loading facilities that did not exist in sufficient numbers. Most critically, the Maus could not be transported by air, eliminating rapid deployment options that characterized modern military operations. Fuel consumption calculations proved equally devastating to the vehicle's operational utility. Technical analysis revealed that the Maus consumed approximately 750 liters of diesel fuel per 100 kilometers of movement, roughly 10 times the consumption rate of conventional tanks. Extended operations would require dedicated fuel convoys consisting of multiple tanker trucks, creating enormous logistical burdens and presenting lucrative targets for enemy forces. The vehicle's operational range, even with auxiliary fueled to approximately 160 tanks, remained limited to approximately 160 kilometers under ideal conditions. American engineers conducting firing tests with captured German ammunition discovered another fundamental flaw in the Supertank concept. While the 128mm gun could indeed destroy any Allied tank at extreme ranges, the massive muzzle blast and recoil forces created problems that German designers had not fully solved. Each shot generated concussive effects that damaged delicate electrical systems throughout the vehicle. The enormous ammunition requirements meant that sustained combat operations would quickly exhaust available supplies, leaving the vehicle defenseless despite its impressive armor protection. The psychological impact of these discoveries extended beyond technical considerations to strategic implications for post-war military planning. American military leaders recognized that German engineering capabilities, estimates in specific, had exceeded Allied areas while revealing fundamental weaknesses in strategic thinking and resource allocation. The Maus demonstrated that technological sophistication without practical application represented wasted potential that could have significantly extended German resistance, if properly directed toward conventional weapons production. Intelligence assessments concluded that Hitler's obsession with superweapons had actually accelerated German defeat by diverting resources from proven technologies that could have equipped larger numbers of conventional forces. The man-hours and materials consumed by super-heavy tank programs could have produced thousands of conventional vehicles, anti-tank guns, and artillery pieces that would have provided genuine military value. Instead, German industry had pursued technological marvels that remained essentially immobile monuments to engineering excess. The captured Maus and its associated documentation provided Allied forces with unprecedented insight into German industrial capabilities and strategic decision-making during the war's final phase. Technical intelligence officers recognized that they were examining the physical manifestation of a regime that had prioritized propaganda value over military effectiveness, producing weapons designed more to intimidate than to achieve tactical objectives. The examination teams worked in shifts around the clock, their portable floodlights casting long shadows across the massive vehicle as documentation continued through the spring nights. Captain Theodore Brennan, a metallurgist from Carnegie Steel who had been assigned to the Technical Intelligence Division, spent days analyzing armor samples chipped from the vehicle's exterior plating. What he discovered challenged fundamental assumptions about steel production capabilities under wartime conditions. The armor plates revealed metallurgical techniques that American industry had never attempted at such thickness. German engineers had achieved uniform hardness throughout plates measuring 8 inches thick, requiring heat treatment processes that demanded enormous industrial infrastructure. Microscopic analysis showed that the steel maintained consistent grain structure from surface to core, indicating temperature control precision that exceeded American manufacturing standards. This level of metallurgical sophistication suggested that German industry had developed specialized techniques specifically for super-heavy armor production. Dr. Margaret Sullivan, one of the few women assigned to technical intelligence operations, had been brought in specifically to analyze the vehicle's electrical systems. Her background in automotive engineering at General Electric provided expertise in the diesel-electric drive technology that the Germans had pioneered for this application. As she traced wiring harnesses and examined motor housings, she realized that German engineers had solved fundamental problems that American designers had considered insurmountable. The electrical leap that would influence American tank development for propulsion system represented a technological decades. Each track was driven by independent electric motors receiving power from a central generator connected to the diesel engine. This configuration provided maneuverability impossible with conventional mechanical transmissions, allowing the massive vehicle to pivot in place despite its enormous weight. Sullivan's technical reports documented innovations in motor design, electrical insulation, and power distribution that American industry would spend years understanding and implementing. However, the sophistication of individual systems could not overcome the fundamental strategic flaws that became increasingly apparent through detailed analysis. Intelligence officers studying captured German production records discovered that manufacturing a single Maus required resources equivalent to producing an entire battalion of conventional tanks. The specialized steel alone consumed monthly allocations that could have equipped multiple armored divisions with proven, reliable vehicles. Major Robert Hayes from the Army's Ordnance Department calculated that the ammunition requirements for sustained combat operations would have required dedicated supply trains consisting of dozens of specialized vehicles. Each 128mm shell weighed over 60 pounds and required precision manufacturing that strained German industrial capacity. The vehicle could carry only 60 rounds for its main gun, providing perhaps 30 minutes of sustained combat before requiring resupply operations that would have been impossible under battlefield conditions. The fuel consumption calculations proved equally devastating to any practical military application. Technical testing revealed that the Maus consumed diesel fuel at rates exceeding 750 liters per 100 kilometers, roughly equivalent to the consumption of an entire American tank platoon. Extended operations would have required fuel convoys consisting of multiple tanker trucks, creating logistical burdens that would have paralyzed conventional military operations. The vehicle's operational range remained limited to approximately 160 kilometers, even with auxiliary fuel tanks, severely restricting tactical flexibility. Transportation studies conducted by Army engineers revealed that the vehicle's weight exceeded the capacity of virtually every bridge in Europe. Movement would have required predetermined routes, avoiding all existing infrastructure, eliminating tactical surprise, and creating predictable targets for enemy air attacks. Railroad transportation demanded specially reinforced cars that existed in insufficient numbers, while the vehicle's dimensions exceeded clearance limits for most European rail systems. The machine that Hitler had envisioned as a mobile fortress would have been essentially immobile under real combat conditions. Perhaps most disturbing were the human factors that technical analysis revealed. The crew compartments, despite the vehicle's massive external dimensions, remained severely cramped due to armor thickness and mechanical systems. Operating positions showed ergonomic designs that would have caused rapid fatigue during extended operations. The noise levels inside the vehicle during operation exceeded safe exposure limits, requiring special protective equipment that would have impaired crew communication and situational awareness. Medical officers examining crew positions concluded that combat effectiveness would have degraded rapidly due to physical stress, noise exposure, and psychological effects of operating inside such a confined, heavily armored environment. The vehicle's massive armor protection, while providing excellent ballistic resistance, created a claustrophobic environment that would have affected crew performance during critical combat situations. Ventilation systems, though sophisticated, could not adequately address temperature control and air quality issues during sustained operations. The discovery of additional technical documentation revealed that the Maus represented only the initial step in Hitler's escalating obsession with super-heavy armored vehicles. Engineering studies found throughout the facility detailed the E-100 program, which would have produced tanks weighing 140 tons with even more sophisticated armor and armament systems. These vehicles would have mounted 150mm guns capable of destroying any conceivable Allied armor at ranges exceeding 4,000 meters. Even more shocking were preliminary designs for the P-1000 Ratte, a proposed 1,000-ton land battleship that defied all conventional understanding of mobile warfare. This mechanical monster would have mounted twin 280mm naval guns in a rotating turret, essentially creating a mobile coastal artillery battery. The vehicle would have required a crew of 40 specialists and consumed resources equivalent to producing an entire armored division of conventional tanks. American engineers studying these plans recognized them as the products of minds completely disconnected from military reality. Intelligence assessments concluded that German leadership had pursued these projects despite overwhelming evidence of their impracticality. Field reports from German commanders had repeatedly emphasized the need for reliable, easily maintained vehicles that could be produced in sufficient quantities to replace combat losses. These requests had been systematically ignored in favor of technological demonstrations that consumed irreplaceable resources while providing no practical military advantage. The psychological impact on German forces had been equally counterproductive. Crews assigned to operate existing heavy tanks had reported mechanical reliability problems that made combat operations increasingly difficult. The Tiger II, which weighed only 70 tons, had already exceeded practical limits for battlefield mobility and maintenance requirements. The prospect of operating vehicles weighing nearly 3 times as much would have created additional stress and reduced combat effectiveness throughout German armored units. American technical intelligence officers recognized that they were examining the physical manifestation of strategic decision-making that had accelerated German defeat. The resources consumed by super-heavy tank programs could have produced thousands of conventional vehicles, artillery pieces, and anti-tank weapons that would have provided genuine military resistance. Instead, German industry had pursued technological marvels that remained essentially useless for actual combat operations. The captured vehicle and its associated documentation provided unprecedented insight into the final phase of German military development. Technical analysis revealed that German engineering capabilities had exceeded Allied estimates in specific areas, while simultaneously demonstrating fundamental weaknesses in strategic planning and resource allocation. The Maus represented the culmination of industrial sophistication applied to militarily counterproductive objectives. Today, only one complete Maus remains, assembled from the captured prototypes by Soviet forces and displayed at the Kubinka Tank Museum, outside Moscow. Visitors still stop in silent amazement before this mechanical monument, struggling to comprehend its enormous dimensions and the twisted ambitions that created it. The machine sits motionless in its display hall, its massive gun barrel pointed toward empty air, its steel tracks forever still upon concrete floors. The American engineers who first discovered this behemoth understood they had witnessed something far more significant than advanced military technology. They had uncovered the physical manifestation of a regime's final delusions, a testament to what happens when unchecked power pursues impossible dreams while reality crumbles around it. The Maus represented not German engineering triumph, but the ultimate failure of strategic thinking, a masterpiece of technical sophistication built to serve no practical purpose. In the decades that followed, those who examined the captured vehicle would reflect on the lesson it embodied. Superior technology means nothing without practical application. Industrial capability becomes meaningless when divorced from strategic reality. The most advanced engineering achievements become monuments to waste when they serve ideology rather than genuine military necessity. The Maus stands today as a reminder that in warfare, as in all human endeavors, the most impressive solutions are worthless if they solve the wrong problems. When American forces found Hitler's experimental supertank in that rubble-strewn proving ground, they discovered more than a machine. They uncovered the final dream of a dying empire, a dream too heavy to move, too complex to maintain, too expensive to produce, and too late to matter. In the end, the heaviest tank ever built became the perfect symbol of the regime that created it. Impressive in its technical achievement, yet ultimately immobile, a monument to ambition that exceeded all practical limits.